I'd like to go ahead and do another example of Lagrange's equations and how you can apply them to different things by studying the pendulum problem, simple pendulum. So we're talking about a string of length L that's suspended from a fixed point, a mass M that's at the end of that string, and the string is inextensible and massless, and then that mass will oscillate back and forth. And we'd like to find the equation of motion using Lagrange's equations. We've found the equation of motion previously using Newton's laws, and that turns out to be a little bit of a painful exercise. With Lagrange's equations, I hope you'll see that it is really, really simple matter. So for coordinates, let me take x to the right, and I want to take y down. And there's a reason for that. When you think about the potential energy of this, so we're going to need the Lagrangian. And for the Lagrangian, we need the kinetic energy. And I'm going to teach you two ways to get that kinetic energy, the dirty way and the clean way. The dirty way is to say the speed of that pendulum bob is omega r. The angular speed times the radius of the circle. It's going in a circle. In this case, omega is going to be theta dot, and r, the radius, is going to be L. So V, the speed, is L theta dot. V equals R omega. Something we've seen before. Substituting this into here gives the kinetic energy and it's correct. It's the other way to find the kinetic energy, and the cleaner way, and the one that comes in extremely well, that will save you from grief, pain, and embarrassment in more complicated problems, is to find the kinetic energy in the following way. V has two components. V is a vector. It has an x dot component and a y dot component. So V can also be written, the vector velocity x dot x hat plus y dot y hat. And V squared is just V dot V. So this is crucial here. You know that V dot vector V dotted into vector V has to equal the magnitude of the speed V, because you can just dot these two together and say magnitude of the first, well, the magnitude of the velocity vector is the speed V, times the magnitude of the second vector, which is also V, times the cosine of the angle in between. But the angle between V and V is 0. So cosine of 0 is 1, and you just get V squared. So this guy here is the same as that guy right there. And this is going to be the key to the cleaner way of finding the kinetic energy. 1/2 m. Now we have V dotted into V. So here's V, vector V. If we dot it into itself, then we'll have x dot x hat plus y dot y hat dotted into that same thing again within parentheses. And we're going to have to FOIL that out. We'll have an x, let's just actually do it. Well, let's FOIL this out. X dot x hat dotted into x dot x hat. Well, what's x hat dot x hat? Well, x hat dot x hat is magnitude of x hat, which is 1, magnitude of x hat, which is 1, times the cosine of the angle in between, which is 0, and the cosine of 0 is 1. So x hat dotted into x hat is just 1, and we just get this x dot squared term. Then we'll have this term dotted into this term. Well, x hat dot y hat, the angle between those is 90 degrees, and the cosine of 90 is 0. So we won't get anything from that. That dot product would be 0. Same thing for this dot product. And then finally we'll get y dot squared out of this one. Okay, and once you've seen where this comes from, you don't have to do this again and again. This is really your starting point for finding the kinetic energy in weird coordinates, in polar coordinates or spherical polar coordinates or whatever. And we'll see more examples of that later on. But we can now figure out what the kinetic energy is for this particular problem, because x and y can be worked out from this equation, or from this diagram. This is x. It's the horizontal displacement of the pendulum bob. Well, x over L is sine of theta, so x is L sine theta. And y L cosine theta. So now all I have to do is figure out what x dot and y dot are. I told you it was a little bit harder, a little bit more work. Well, x dot, what's that? L is a constant. X dot means the time derivative of x. And so we're going to need to take the time derivative of sine theta. Theta is not a constant. It's obviously changing as the pendulum moves back and forth. Theta is a function of time. And the derivative of the sine is the cosine. And since we're taking the derivative with respect to time and not theta, then we have to take the derivative of the inside of the sine. So the derivative of theta with respect to t is theta dot. So that x dot is just going to be L cosine theta times theta dot. So that's this x dot squared right here. Y dot is a similar matter. We want to take the time derivative of y. L is a constant. Derivative of the cosine is minus the sine. Derivative of the inside is theta dot. Minus L sine theta times theta dot. And finally, we can see what we get. Notice in both of these terms we have an L squared. This minus sign cancels. Well, minus sign squared becomes a positive sign. We have an L squared that we can take out. Do that up here. One half m. I'm going to factor out this L squared here and here. I also have a theta dot. Notice this theta dot is not inside the cosine theta. So it's cosine theta, parentheses, times theta dot. Theta dot squared appears in both terms. And then what we're left over with inside these big parentheses is cosine squared theta plus sine squared theta. And I think you'll agree that that's 1. So this is, luckily, the same as that. And this is kind of the quick and dirty way of doing it. This is the longer and clean way of doing it. And if you want to be really careful, it's usually a good idea to do it both ways to make sure you've got that kinetic energy right. Because believe you me, it's easy to get the kinetic energy wrong. I've done it before. And you probably will do this in your future. All right, that's kinetic energy. That takes care of this in the Lagrangian. Potential energy is no big deal. It's mg times, and let me be careful, mgh, where h is measured vertically upward. Well, we have something that's measured vertically, it's y. But unfortunately, it's not measured vertically upward, it's measured vertically downward. So if we want to have something that's measured vertically upward, then we can just simply say that h is minus y. And substitute that in here, and we get that the potential energy is minus mgy. That's a gravitational potential energy for a mass that's in a uniform gravitational field. And the minus sign there is a little weirdo, but it's only because we took y in the minus in the downward direction instead of taking it normally in the upward direction. And the reason for taking it down is just to make this part of it easy. All right, we have t, we have u, we can find L. Well, Merry Christmas, because that's 1/2 ml squared theta dot squared. And then we're going to subtract u. Well, u already has a minus sign in front of it, and so when we subtract u, it ends up being positive. And we actually know what y is. Y is L cosine theta, so we can so now we're just taking the negative of this, putting it in here. So that's mg L cosine theta. There's a Lagrangian. Well, so now we want to try and find the equation of motion. How do we do that? And the answer is Lagrange's equations, dl by dq. So we're going to need a generalized coordinate for this problem. And the best way to do it is just to see what kind of the Lagrangian, how it's shaking out, and see what it depends on. But clearly the Lagrangian depends on theta and theta dot. And doesn't depend on the time explicitly. So theta is a pretty good choice for a generalized coordinate. So when you write Lagrange's, and in fact it is a great choice. So this is dl by dq. Well, this is going to be theta. We're just going to say q, the generalized coordinate, equals theta. And plug that into Lagrange's equations. It's dl dq minus d by dt, dl by dq dot, but q is theta, so that's it. We just have to take these derivatives now. dl by d theta, let's see if we can take that derivative. The derivative, these three are constants. The derivative of the cosine is minus the sine. And let me write that out, dl by d theta. Okay, we're taking the derivative of L with respect to theta while holding theta dot and perhaps the time constant. So this is a key point. I'd like to get your attention at this point. dl by d theta dot is, we're only going to get a contribution from this term, not from this term, because theta dot is being considered as constant while we take that partial derivative. And the only theta that appears in the second term is in this cosine. Derivative of the cosine is minus the sine. And there is a huge temptation for students and professors alike to say, okay, well, I've got to, just like I did over here, when I took the derivative x dot, I had a cosine theta times, I had to take the derivative of the inside. There's this huge temptation to pop a theta dot right there. But you don't need it. And in fact, it's wrong. Remember that this is not a time derivative. This is a derivative of L with respect to theta. So we're just thinking of this as a function of theta. I'm going to take a derivative of cosine theta with respect to theta. That's minus sine theta. You don't have to take the derivative of the inside. So you're done. That's dl d theta. And then dl d theta dot. Same kind of deal. We'll get a contribution from this term, 1/2 m L squared, and then the derivative of theta dot squared with respect to theta dot is just 2 theta dot. And now if we plug these into Lagrange's equation, hopefully we'll get something that will make us all happy. dl by d theta, that's minus mgl sine theta, that's this term, minus d by dt, dl by d theta dot. Well, this 2 can cancel this 1/2, and we just get ml squared theta dot. And that's all supposed to equal 0. I'm going to divide through by m, and I'm going to divide through by L squared. I'm going to divide through, no, that's it. And I'm going to take this term, the d by dt term, over to the left-hand side, and take this derivative, d by dt of theta dot will give me theta double dot. So what do we end up with? This term went over to the other side of the equation, so it becomes positive. This term is still negative. And what do we have left over after we divide by mass? Mass is canceled here. We divide by L squared. We'll get GL over L squared. That's minus G over L. And that, my friends, is the equation of motion for a pendulum with arbitrary amplitude. It can go out as far as you want it to go. If you want, for small amplitudes, theta much less than 1, then the sine theta can be approximated by theta, and theta dot is minus G over L theta. So just a couple of takeaways from this. First of all, be careful about taking these derivatives of L with respect to theta, and remember that you're taking it with respect to some generalized coordinate, in this case theta, and you don't have to take the derivative of the inside. Also, be careful about finding the kinetic energy. This quick and dirty way of finding the kinetic energy would have saved us a lot of effort, all of this effort here and some extra derivatives. And it's fine in this simple case, but in more complicated cases, you're better off doing a little bit of algebra, writing out x and y in terms of the generalized coordinate. That's what these two relationships are here, where we've expressed x and y in terms of the generalized coordinate, and then starting from here to find the kinetic energy. You know this is right. It's in Cartesian coordinates. It's as sure as the day is long that that's going to be right. Take the derivatives of these two guys, plug them in, and find out what the kinetic energy is.